Okay, I'm Joe Hirako from Kyoto University, and I'm a magic member in Japan. Last December, there was the first detection of the FSRQ TON 599 in very high energy regime, and I'll talk about that. And thank you for allowed me to talk about this. This is outline, and firstly I'll talk about the general things of FSRQs, and then I'll introduce the TON 599, and then I'll show our analysis results. Okay, then FSRQ is a laser with strong optical emission lines, unlike flux. And they are very luminous, so we can observe them if they are at very high redshift. So it would be good proof for indirect measurements of EVR as the previous presentations. And they are intrinsically more powerful than VLux. This is the SEDs of FSRQ and VLux. This is FSRQ SEDs, and these are low VLux and high peak VLux. And they have lower frequency peaks than VLux, and the ratio of the synchrotron peak and inverse Compton peak is the inverse Compton peak is dominant. So because of the synchrotron cooling, so they have lower frequency peaks. Then they have a variability in a wide range from radio to very high energy gamma rays. And so we can constrain the emission region from the variability. Okay, I'll skip that. Then about EVR, okay, also I'll skip about this. And but the important thing is the effect of EVR absorption is relevant only above tens of JeVs, like here. And the tens of JeVs gamma rays don't affected by EVR. So we can estimate the upper limit on the EVR distribution, EVR fluxes from the comparison between observed spectrum and maximum spectrum from theory. So if we can understand the EVR distribution and evolution, it leads to the understanding of cosmology like star formation rate to a galaxy formation. Then go back to FSRQ. So the problems, one of the problems of FSRQ is where is the emission region? So gamma ray, very high energy gamma ray emission region. So the possible candidates of the very high energy gamma ray emission region is the first within the broad line region, or in the radiation field of dust auroras, or near the radio core. So if it's closer to the supermassive black hole, so it becomes easier to explain their variabilities and luminosities, but it becomes more problematic, the absorption of subatomic gamma rays. Then this is an example of the constraints from variability. Then this is light curve by magic of PKS 1222, and this is FSRQ at the redshift is 0.4, and this shows the very fast variability light curve between this point and this point. So then we can define the T-var like this formula, and the Fi is ice flux of ice points, and the Ti is the time of ice points. Then so we can define T-var like this, and so we can calculate from using this T-var the emission upper limit of the emission region radius, like this. So we can constrain the emission region from variabilities. Then this is FSRQs in VHE sky. in GV band, the VLux is about this, and FSRQ is about 500 sources. But in TV range, the FSRQs are only 7 sources, these red points. Then this is 7 FSRQs. This main topic, the TON 599, is the third farthest source in very high energy sky up to date. Okay, let's go to TON 599. Okay, this is another names. And this is detected on the last December 15th by magic, and this is 8 years of that, and soon after confirmed by Veritas. Okay, and so the redshift is 0.7, and this is the fastest source, and so this is the seed square plot of the discovery day, and so we detect the 10 sigma signals for about 1 hour. Okay, so let me introduce the past studies in Lady Band about TON 599. Okay, a long-term observation was conducted by the Umurao Observatory, and it was about 3 decades. Then this is the light curve of the 3 decades in radio band, and there are 3 radio bands. And so in this paper, they did a full analysis to this light curve, and the 4 periodic components was found like this, and these correspond to the frequencies of 1 to 2 to 3 to 4. So this seems to be the quasi-harmonic oscillation. And these harmonic oscillations also found in these phrases. And so this harmonic oscillation is derived from the propagation of the dynamics of a accretion disk, but it is not still unclear. Okay, let's go to our work. This is an instrument used in this study, and the first magic telescopes is there 2 stereoscopic system of 2 equal sized IACs, and the energy threshold is above 50 GeV, and the WEBT is whole Earth laser telescopes, and this is a network of optical and IR and the radio observatories. Also, the Fermi-LAT is a satellite observatory, and the energy threshold is above 100 MeV. Okay, this is a light curve of in VHE by magic of TON 599, and so this is above 80 GeV and daily light curve. So we detect them on December 15th, and observation was continued to December 29th. So the flux was peaked on the second day, December 16th, and it corresponds to about half of Crab Nebula units. Then the flare faded, and we decided to separate them into 4 subsamples, like period A, and period B, and period C, and period D. Okay, then this is a multi-wavelength light curves by magic and Fermi-LAT. This is flux, and this is photon index, and optical flux by the WEBT, and polarization, and EVPA, and radio flux. The Fermi flux shows a similar light curve or to the VHE light curve, and also optical flux is similar to this time evolution. But the polarization decreases, and with this is peaked, but after the flare, the polarization showed the increase, but then radio flux is no significant change. Then this is Fermi and magic SEDs for each period A and B and C and B. So there are 4 plots in this figure, and this is Fermi-LAT points, and this is the solid circle is magic observed points, and hollow circles are the intrinsic points by using EVR model. And the red line is the fit for observed points, and the dotted red line is fit for de-observed points. And then we can see the effect of EVR absorption. Okay, then, so these 4 figures are all same ranges, so we can see the variations of SEDs along with the light curves. Okay. Then this is the last results of analysis. This is multi-wavelength SEDs. This is radio points and infrared and optical points and X-ray. This is data and Fermi data and magic points. So we used SSC and Extragalactic model, and the synchrotron emission dominant to the low energy band, and synchrotron, self-synchrotron inverse components contribute about 550% in X-ray. Okay, and these are assumptions. So we assumed emission region is outside of broadline region, and the distance of very high energy gamma ray emission region is 10 times emission region radius. Then we use these values. Then these are modeling results, and the interesting thing is the Bark-Lorentz factor of the emission region is faded along with the light curve faded. So jet slowing down as flare fades out. Then, okay, this is summary of this talk. So the TON 599 is FSRQ and received at 0.7, and it is the third fastest source in which range. So it was discovered on the last December 15th, and the flux was peaked on the December 16th, and it corresponds to half of Crab Nebula units. And so then flare faded. Then flux in very high energy and optical flux changing with the same trend, but polarization decreases with the flux and jump in polarization degree after the very high energy flares. So then in modeling, the jets slowing down as flare fades out. So in next, we will discuss about these results, and we will try another modelings to multiwavelength SEDs. And we now writing paper, so please be looking forward to the paper. And that's all. Thank you for listening.